So up next, we have a panel Huddle, Interdisciplinary Approaches to Solving Global Challenges. The panelists for this session are Professor Wendelin Werner, Professor Dame Sue Black, Professor Takaaki Kajita. Moderating this session will be Associate Professor Sieren Lim from Nanyang Technological University. And Prof. Lim is an Associate Prof of Bioengineering at the School of Chemical and Biomedical Engineering and the Associate Dean for Global Partnership at the Graduate College NTU. Let us welcome our panel and moderator. And now hand over to Prof. Lim.
Okay, good morning, everyone. I'm very happy to see many exciting faces this morning. And I'm even more excited to be here moderating this panel. It really is my first time actually moderating such panel. So this panel is specifically discuss a interdisciplinary approach that will transcend humanity. So from my own experience, my name is Sieren Lim, and I'm actually have been one of the third batch of students who came into an interdisciplinary program when I was doing my PhD a while ago. So then, but that particular concept have actually been the concept that people have used and then learn about how to do properly. But we didn't have really training for that, right? So, but then this research, this interdisciplinary concept is very important. And then you will hear it from each of these prominent scientists on how important that is and how we can actually leverage on it and then into our own work, into our own research as well. So today I'm joined by three prominent scientists. The first one is over there, Dame Sue Black. She grew up with her dad hunting rabbits and stuff. So then, so she's very used to having blood all over, and and which basically, based on her biography, led her to be very comfortable in looking at human parts, and that brings her into her love and exploration into anthropologic forensic. So then, from there, she has to identify different, specifically in the time of war, where you really want to find your loved ones you might have lost. And then from there, she would try to figure out from very small parts that she could find who this person is, bringing closure to the people who have lost their loved ones. So it's very important work, but of course, it also is taxing for the person who's actually have to figure out what these particular parts come from. So then she actually used interdisciplinary research to enable her to do her work and also to help the people to figure out what these parts are. So I will let her discuss what her work is, and then what is the biggest challenge that she is facing in her field.
Wow, okay, thank you very much indeed. I don't know why I'm here, because in terms of being a scientist, I am what's called a gutter scientist. I'm a street scientist. I work in the forensic field. I'm not in an academic ivory tower anywhere. When something horrendous happens in the world and people lose their lives, then that's often why I'm called. And sometimes the bodies that we deal with are very badly decomposed or very fragmented. And the interdisciplinarity of a team is incredibly important, because when you go into a mass fatality situation, whether it's in a war zone or it's following a national a disaster of some sort, you don't know what it is that you're going to encounter. So we will have a team that will be made up of a number of individuals with expertise. So we're very used to knowing that we're a small cog in a very big wheel. When it comes to the research that I do, part of our problem really was identifying what is a global crime. And it's not a comfortable crime, and I apologize for discussing it here. And given the number of individuals in this room, some of you will have been affected by that crime. And the crime is child abuse, and in particular, child sexual abuse. And what I do is I look at the images and I look at the videos of this abuse. And frequently, the perpetrator and parts of the perpetrator are included in that image. And often it's the back of their hand. And the question posed to me in a case many years ago was, can we identify who the perpetrator was in this abuse just from the back of their hand? And we're used to the palm of the hand because it's where we have our fingerprints and our palm prints. But the back of your hand, what's identifiable about the back of your hand? I love the fact that the scientists in the room are looking at the back of their hand because you brought your own Petri dish. Here it is. Have a look at it. Look at the person who's sitting next to you. Your vein pattern is different to theirs. In fact, your vein pattern on the back of your right hand is different to your left hand. Look at the skin creases, the pattern of creases over your knuckles. It's different in every single finger. If you've got little punctate pigments, so freckles or liver spots, you're not old enough to have liver spots, then they're in an entirely different place. And we realized that the back of the hand is probably, and I still use the word probably because I'm a scientist, unique. And so we started a project many, many years ago involving a really large data set, mainly of police officers, because we had them as a captive audience. And so we created a database out of them. And we were able to show that when you look at all the anatomical features that we can see on the back of the hand, we think it is a unique multimodal biometric. And that's really incredibly important in terms of identification of perpetrators. Because if you're going to accuse somebody of abusing a child, then you need to have a high degree of certainty that you're accusing the right person. But I know what the problem is, I just don't know how to solve it. What I need are the mathematicians, I need the bioinformatics, I need the computer scientists, I need the people who have the skill set that I don't. And I have a very, very mean and nasty research team because they play a game on me. And what they do is every time we have a board meeting, they take a bet on how long it will take in the presentations before I no longer understand a word that they are saying. And the last time we had a board meeting, I was on slide number 2. And that's where the interdisciplinarity works. You don't have all the skills yourself. You have to rely on the others to be able to do that. We're about to publish fairly soon, and I have to say, and I'm not giving it away, but the statistics on the potentially uniqueness of the hand is phenomenal and way exceeds what we ever thought was possible. It could not have been done by one person. It has to be done by a team. And the biggest challenge is that this is a crime that is global, and it's a crime that is shared globally. No longer does it happen within the borders of any country. We have to be able to work across country borders. And it's a crime where the individual who's found guilty may have a custodial sentence. They may go away for a few months or a few years. But the victim of that crime lives with that crime for the rest of their life. It's significant, it's important, and the impact that it has on the psychology and the psyche of the victim is long-lived. And for me, that's a really important thing. If science in any way can bring a little bit of closure to somebody who has suffered to that extent, then we've done our job.
Thank you, Professor Dame Black. Very, very important opening to this panel. And because of that, she has won many, many awards. And now she's also the president of the St. John's College at Oxford. So the next professor that I'm going to introduce is Professor Kajita Takaaki from University of Tokyo. He is the Nobel laureate in physics, and so he actually works on an object that is very far away. So Dame Sue Black was working on something that is really right here on Earth, and then Professor Kajita is working on something that is far away. And he likes to gaze on stars. And that sort of like bring him to many explorations in space. And one of the important experiments that he had kind of coined the the very important finding from just out of passion again, looking at the nature, is this groundbreaking discovery of neutrino oscillations that prompted reevaluation of the standard model. What is the standard model?
Okay, thank you. Well, standard model is a model that describes elementary particles and their interactions. Actually, in the standard model, neutrinos are assumed to have no mass. But, well, what we found was neutrinos have very small mass, and this implied that standard model is not the perfect model. We may have to improve the model in the future.
Thank you. So what is then the biggest challenge you see in your field at the moment that, that you're very excited about?
Well, thank you. Well, actually, okay. I used to work on neutrinos, and now I'm working on gravitational waves. I think I'm, say, cosmic ray physicist or an astroparticle physicist. And, well, actually, in our field, we have many exciting challenges. Therefore, I think I cannot select one most exciting challenge. So instead of selecting one, I want to list
Sure.
the challenges we are excited. Well, for example, we know there are dark matter particles. Well, actually, the dark matter is much more dominated than the ordinary matter. But we do not know what are dark matter particles. So we definitely want to know what are dark matter particles, and this is, in fact, a very important challenge. But this is just one of them, I would say. Well, okay. Next one is the cosmic rays. Well, cosmic rays are, say, high-energy particles, protons, or heavier nuclei, such as helium or even iron. And some of them are accelerated to up to, say, 10 to 20 electron volt. And energy, well, I would say similar to the kinetic energy of a professional baseball pitcher's first ball. But we do not know where and how these particles are accelerated. So this is another challenge. And, well, I said I used to work on neutrinos. And in fact, neutrino seems to be really a special particle. But we do not understand why neutrino, for example, we do not understand why neutrino mass is so small compared with other particles' mass. So we really think maybe neutrinos are indeed special particles. So I think we have to study more on neutrinos. And finally, coming to my present challenge, I'm working on gravitational wave project called Kagura. The field of gravitational wave is new. The first direct discovery of a gravitational wave signal was about 10 years ago. We do not know what kind of new discoveries are ahead of us. So, well, we do not know what will be the exciting new challenges in gravitational waves yet. So, well, that are just a few examples, but there are many exciting challenges in our field.
Okay, thank you, Professor Kajita. How many of you actually understood 50% of what he said? Okay, so that is the most important lesson. I think Professor Su was lost in the second slide at the board meeting. And then I think we need to learn a lot about the other discipline to actually appreciate what they are actually working on. I think that's sort of a very important point here, that there are a lot of exciting things, challenges in each field that we probably are not aware, but we should. right? And try to break away from our own discipline and then try to reach out to the others and then see what is actually going on. It might be very exciting. And we have just too ignorant to figure that out at the moment. Yeah? So after this panel, hopefully that you will be able to get more excited about the other fields. So I think the two previous speakers or panelists have mentioned something about probability. There is something probable, and then there's also a lot of probabilities involved in your work, right, Professor Kajita, in understanding the universe and the atomic matters. So then it comes to our third panelist, Wendelin, Werner, who is actually doing a lot of work on probability. and one thing I actually found that he has, Singaporeans like numbers, right? So we like to rank everything. We like to see who's actually number 1, 2, 3, 4, 5. And then impact factors are also part of our evaluations. And Wendelin has a very interesting numbers that is attached to him. And that number is, let me see, the number is number 6. Anybody heard about something called the Erdos-Bacon number? No? The Erdos-Bacon number is the number that correlates a scientist to the entertainment industry. The smaller the number, the closer they are to David Bacon. So with that, please tell us, what is the hardest or the most exciting challenge in your field?
Okay, so
Probably.
thank you very much. So first of all, about this Erdos-Bacon number, let's get it out of the way. As you know, there is this small world theory that, anybody, you have shaken the hand of somebody who has shaken the hand of the Pope, or somebody who shakes lots of hands, and it usually is very, the number of, the length of that chain is sort of usually very short for most people. So when you're a mathematician, if you wrote a paper with somebody who wrote a paper with Paul Erdős, who famously wrote many papers, then you have a Erdős number 3. And Bacon is a famous actor who shoot many movies. So if you did a movie with somebody who did a movie with Kevin Bacon, then you have a Bacon number of 3. And then you add them up, and it gives a Erdős-Bacon number. And as a result, from what I just said, if you did write a paper with somebody else, and if you were part of a movie, then you're very likely to have Erdős-Bacon number 6. There's nothing special about having a Erdős-Bacon number 6.
So he's just telling you that he has been a movie star.
But I remember, just to get it out of the way, the one that was when I was a teenager, completely by accident. I ended up being part of a movie. And at the end, I definitely said, I don't want to be an actor. The main reason is that I don't want to be famous. I don't want to be on stage, giving life lessons to people, feeling unqualified about and being scrutinized. I want to do my science in my corner. Oh, okay, then life has its twists, and now I'm here with a microphone in my hand. But, okay. Now let's go to mathematics. As you'll see tomorrow, if you wake up early enough for my lecture, it's always a challenge for mathematicians to, describe to, or say pure mathematicians to describe what we're doing, why we're interested in what we're interested in, and what the challenges are. So maybe I can say a few just meta answers about what the biggest challenges are in our field. Of course, you could point to specific questions like the Riemann hypothesis, or these are very open questions that people have been thinking about for many years. And there are, spectacular things happening every year in different parts of mathematics. On the other hand, I think the two important things, what the important challenges for our field are, is of course, the first thing is, what makes the value of a mathematical result, right? So why do we say this is important, this is not? Well, the value is always in the proof. It's not about, the end result, it's how you get there. It's like you do it's not climbing that mountain, is, what sort of route are you following to climb that mountain? Are you making it, is it very convoluted with lots of twists and very clever turns? Or are you actually, completely simplifying everything and discovering a new mathematical object that will actually, the beauty of it would be somehow the goal of the aspect. And so in some sense, it's just the challenge is to continue exploring and finding, new mathematical structures that would enable us to get somewhere. The other aspect I want to maybe emphasize here, because I'm not sure I'll have the opportunity to say that, and it relates in some way to interdisciplinary, is that even within mathematics, there is because it's a field that has been expanding a lot, there's a lot of specialization of, people working, specializing very early in one pretty narrow part of mathematics, and that the number of mathematicians who have, sort of a slightly broader vision of actually why are we doing this, what exists elsewhere, how can we connect it with other parts of mathematics, diminishes a lot. And the way research is sort of structures these days is that, you have to publish quickly, and, and in mathematics, the ideas come a lot from actually reading very carefully papers and proofs by others, which is not something that is actually valued, at all. You can't write in your research report, I spent 6 months of my life, reading, understanding that proof. That would be considered a waste by the funding body. But that's actually the essential thing, that we have to continue to be able to take the time to actually read and listen to what the other mathematicians are doing, and not just the results, but actually the path, which takes longer. And I can just say an anecdote that we had some years ago, one president of France, who's now under trial, invited mathematicians to hear about how we think how our world is. And at some point I made the point that, that sort of point, I said, that person who has been at this GYSS some years ago, Ngo Bao Chao, he got this big prize because some other mathematicians took 6 months of their lives to actually check that his proof was correct. And then suddenly we realized that we were somehow in a somewhat different world than the rest of humanity, because then the president said, but why 6 months? And then all the mathematicians around the table laughed, and one of them said, because it's hard, Mr. President. And I think that this aspect of not jumping to conclusions and being slow enough and keeping to okay, so that was my non-answer to your question.
Well, thank you. That was provides a lot of insights as well in terms of, I'm always fascinated on how each one of you going through that process of discovery, right? So from you trying to understand the proof, how do you get from looking at the mathematical problem to actually coming to the proof? And somebody else even have to understand the proof and then make sure that the proof is correct. I think, again, it highlights further that a relationship with the correct politician could also be very important there. And again, they are not familiar with all these projects and works that the people are doing, but it's very important to understand them, or try to understand them. All right, so this is an interdisciplinary panel. As you know, that all the panelists have mentioned that in one way or another. What I would like to understand also is that whether there is a different flavors of interdisciplinarity. So what is interdisciplinary studies or interdisciplinary fields? Is there even such things? So that would be my question. So Wendell, would you like to come first, or? Yeah.
Well, I mean, there there are as many scientific views or history about sciences that there are scientists. So, each of us went through our own personal path. And so what I can say, of course, is that for the part of mathematics that I am involved with, there are very naturally two, apart from, being interdisciplinary with talking with other mathematicians, some part of what we did with was building on ideas of a mathematician called Ode Schramm, who was able to link two parts of mathematics, which is complex analysis and probability theory, together in a very essential way. So you can have interdisciplinary, within actually, a science that has become somehow split. But more generally, I think, mathematics has been fueled by physics questions and ideas for centuries. And it continues to be, one of our main sources. And, okay, we have this week a number of physics Nobel Prize laureates, and I certainly, can relate a lot to what some of them have been doing. And we, sort of, I guess even in the Fields Medal, the justification, they mentioned conformal field theory as, one of the items, which actually is a physics thing. So, but maybe I can say two general statements. The first one is that I try often to explain to our funders, who always want to insist on interdisciplinary, that it's not a goal, right? It's a tool to understand something. So, doing a programmatic interdisciplinary, a priori statement is not, a goal. And of course, you can relate two things together if you have expertise in both fields, not just by picking, randomly something that you don't really understand deeply about. So that can be either discussing with somebody else from that area, if that works, or actually have the expertise yourself. Now, I think maybe one, I'm going to, as you see, I like twists and saying the things, maybe putting it the other way around, is that my personal experience was very often, say, discussing with the physicists who were doing these, elaborate field theories with amazing results, using very, very complex mathematics that I wouldn't understand myself, was always, say, there should be, ought to be, I want to understand it in my way. And a number of mathematicians tried that, and it always felt that, they were going to talk to the physicists doing conformal field theory, a bit like, missionaries, sent from Europe into a faraway land and trying to teach, something to explaining to the other people, and then they come back. And when they come back, they speak the other language, and you don't understand them anymore. They became physicists. And so sometimes, occasionally, I felt like, in order to make this interdisciplinary thing, sometimes also you need to just not listen to the other side, but, try to stick to your own approach, which might not necessarily be fitting to the curriculum or that was common in the other area. And so that brings me to the other aspect, which is that different disciplines, somehow the rules of the games are different, and also the rules of success or what is an important result or something like that is different. What the goal is also different. So if you are a physicist, you want to develop a theory that will then, be validated by actual experiments. That's sort of in some sense, if you're a mathematician, you decided to live in the abstract world anyway. You don't care really about the reality. You just want a nice, beautiful mathematical object. And sometimes the fact that the rules of the games are different makes that people are trained, the brain, and we want to succeed and we want to, adapt to the rules of a given field. make that if you come from outside with a different perspective, because you have also, value more other aspects of, the questions and what you're after, can help you to, make the bridge. So as you see, my own perspective of the interaction is, of course, you are fueled by the discussions or the input or what you can read from the other side, but it's sort of still a very individual-based mathematician's approach, which is like trying to understand things yourself in the way you want to understand them for your own satisfaction. That's why it's sort of a bit the way we tend to. Yeah.
Okay, thank you. So that was a very interesting take on what is interdisciplinarity. I thought interdisciplinarity would be like from physics and maybe biology, and then he's talking about interdisciplinary within the fields of mathematics. And I thought that was a very interesting take on that. And again, he does not just look at mathematics on its own, but really looking at problems maybe that is presented by other fields. In this particular example was physics.
Yeah. I would like to add maybe that one main source of questions these days as well, for probability theory oriented things come from computer science, and here again we have lots of eminent representative here. In that case, somehow there's less of a cultural split, in some sense, in terms of the rules of the game and what the questions are, so yeah. Just wanted to.
Okay, so depending on what the other fields are, the different languages is probably not as far away as you might think. Okay, all right, thank you, Wendell. We're going to go to the next panelist, Professor Kajita. How do you define interdisciplinary?
Well, okay, thank you. First of all, I have to tell I'm an experimental physicist, and therefore, well, essentially, I do not have any personal connection to mathematical people. I'm sorry. Anyway, yeah. Well, first of all, I want to say it's not possible for me to define interdisciplinary approaches. Therefore, I just want to mention just one example in our field where the interdisciplinary approach is important. Well, as I said, one of the challenges is the understanding of the origin of the cosmic rays. We'd like to know where and how these extraordinary high-energy particles are accelerated. Well, in order to know the origin, you have to know from where the particles come. But the problem is, if we observe the direction of these particles, cosmic ray particles, even if we very accurately measure the direction they come, it's not possible to know the origin, because there are galactic and intergalactic magnetic field, and therefore these particles are bent. So we have no way to tell the origin by observing the cosmic ray particles. So we have to think some other ways, and the very important thing is to observe other particles, neutral particles, and they are gamma rays and neutrinos. And these particles, gamma rays and neutrinos, are produced as a kind of byproduct together with the cosmic rays. And therefore, if we observe the direction these gamma rays and neutrinos come from, we know from where they come. But, well, since they are the byproduct, we have to understand the processes in very detail. Therefore, we need the help from, say, theoretical people or people who do extensive simulations. So, by combining all this information, we are hoping to come to know the origin, but we are not yet. In any case, typically the problem we are facing now, not only pure scientific field, but also various issues in the earth, cannot be solved in any simple ways. So I think we need interdisciplinary approaches.
Thank you, Professor Kajita. So in your field, in that particular sentence you mentioned, what other field would you think that, to help in terms of solving problems in your, in your field, other fields that could be interdisciplinary?
Oh, well, actually, in many fields, I think interdisciplinary approach is very important because, well, nowadays, even if we get the data, we need to have a precise interpretation of the data. And for this, we need different people working on theoretical side. So always, we have to work together, theorists and experimentalists.
Does it include mathematicians?
Well, I don't know. Sorry.
Okay, thanks. Thanks for the honest answer. So let's move on to Dame Black.
So you see, it's really interesting, and it's very easy from my perspective, because anatomy is the oldest science in the world. So we know we have supremacy anyway, because we're a narcissistic primate, and since the dawn of man and the age of man, we've looked at each other and we've looked inside ourselves. So I have a problem with Linnaeus. Linnaeus is my problem because he decided to feed into our narcissistic human personality of classifying things. So we put people into disciplines. What a dreadful straitjacket to be in, to be a mathematician, or to be a physicist, or to be an anatomist, because it's a boundary and it limits you. And I have a real problem with that. So if you think about any of these disciplines being like a silo, as you get to the core of the silo, then there's less space. And the individuals who are there don't move around as much. They're part of the clan. They stick together. But as you get out to the outside and there's a bit more room, they get a bit more excited and they get a little bit more different to what's right in the core. And I'm not really too worried about the core, because that will always exist, because there will always be boring scientists. But what I'm interested in are those who are getting really excited out towards the periphery. And when you put a group of people like this on a platform, you're always going to learn something. So I knew nothing about the number, the name that I can't remember now, but I knew that it came to Kevin Bacon, because I could remember the actor but couldn't remember the mathematician, is that I realized that I must have a really low number, because I'm going to name drop here, which is one of my dear friends is Alan Alda, who's the actor who's Hawkeye and MASH. And Alan Alda always said to me, because he's a great believer in science, he says, the most exciting place is a threshold. Because at a threshold, you step from one world into another. And in the world of movies, they use that incredibly well. Columbo, who was the detective, would always leave the room, and just on the threshold, he'd turn around and come back and ask the killer question. So the thresholds are where excitement is. And that boundary where an anatomist meets a physicist, where an anatomist meets a mathematician, that's the exciting bit. Not the bit in the middle, because that's really dull and that's really boring and I don't want to be there. But I want to be at that threshold where something that another scientist says to me sends your mind off in a complete and utter tiz, because you've never thought that way before. That's where interdisciplinarity comes in. It's the magic, it's the excitement of somebody knowing something that you don't know, but them knowing it and relaying it to you changes your world. That happens just a handful of times in our life as a scientist, but I'll bet any scientist in this room who's had that will remember when that happened, because it is absolutely pivotal.
Beautifully said. I was like giving some chills on my spine just now, but yes, so in that case, so you're talking about, you keep your core, but always be on a threshold.
Oh yeah, but if you're going to choose, you want to be dancing with some space out at the edges, meeting really interesting people at thresholds. You don't want to be in a room with anatomists. You really don't.
Okay. All right, so Wendell has, please go ahead.
I feel I have to say one word, which is, you know, the random structures I've been working on, and lots of physicists have been working on before, are exactly having to do with the things that occur at phase transition points, which is, you know, exactly when you are at the threshold between, you know, phase transition between two macroscopic deterministic features. Well, if you zoom in at this phase transition point, then something exciting happens, because then randomness shows up, which is at this boundary. Then you have some universal, you know, random structures that emerge. They are random, but yeah, so they are the core of what we are, you know, interested in, which is why randomness shows up in lots of cases in sort of physics questions. Yeah, so I agree that, you know, it's very exciting to look at these random things that happen at these interfaces.
Yeah, it's very interesting that, you know, the way that you talk about boundaries and differences, that, you know, threshold is very different from different fields, right? So Sue was talking about the boundary between anatomy and physics, and then you're talking about these random walks and molecules, I guess, also moving around, and probably Professor Kajita is talking about the boundary of the universe. That's somewhere else. And yeah. So anyway, before we move on to the next topic, I would like to invite some burning questions from the audience. I'm pretty sure some of you have some of those in there. Is there any burning questions before we move on, talk about other ones? I saw hands up over there. Please go ahead.
Hi, my name is Revati. Really great meeting all of you guys in this session. I am a bioengineering student, and this is something that I've always pondered a lot about, although bioengineering is an engineering degree, there's always a lot of overlap between science, like biology and engineering in our field, and I've always had to work with people from biology and engineering in the same room, and a lot of times trying to mediate the type of mindset they have has always been a trouble that I've had. And here we have quite a number of engineers and scientists coming together, and I'm wondering, how do you kind of let these two people communicate and work on something in common? Yeah.
Okay, so I think, Revati, were you in my class?
Yes.
Okay, so I taught her something about boundary conditions too in engineering discipline. Okay, so let's take the questions. Any of the panelists would like to take that? How do we bridge that discipline when we're engineers and scientists are working together, or mathematicians, physicists working together?
I think the point is it's really difficult. And because it's difficult, that's what makes it interesting. If it was easy, everybody would have done it. And trying to get people to speak the same language and to think not necessarily the same way, but to at least along the same track, that's what's the real challenge. With my team, I find it usually involves copious amounts of cake. So the more sugar that I can give them, and the more relaxed they feel, the more they open up, they stop pretending to be a core scientist of something and just riff with ideas. If you can get into the riffing phase of ideas, then I think you overcome a lot of those boundaries and those barriers. But it's not easy, but it is really worthwhile pursuing.
Any other comments?
Yeah, I mean, it's a tricky question, especially for me, because I'm not really often discussing with people who want to produce something in an engineering way. But I think, I mean, one main problem is, I mean, there are two layers. The first one is sort of the vocabulary, the description of the problem, and so on. And the other one is, you know, what the goal is. You know, you want to quickly, you know, get an idea, quickly produce something out of it or not. And I think one of the key aspects of when you are going to interact with people with different mindsets, which I think one should not underestimate the difficulty of, is that you need a lot of trust, mutual trust. You know, that if you give your idea to the others, you make sure that they're not going to run away with whatever you give them to do their thing and capitalize on their side. Because so I think that there's that element which is very important in sort of the interdisciplinary matter, and especially because sometimes it's very difficult for us to, when you have an idea which comes from outside, which is going to be valued on the other side, to actually really value it. To say, oh yeah, okay, we didn't have that perspective on things. We accept that the other side did bring really something new, and so one has to not just take from the other side, but give, and also accept that some things might drift away from what one is doing. But I think that aspect is, I think, very important. And
okay, thanks. Trust is a very important currency in interdisciplinary research. Yes. So any more comments? No? Any more questions before we go on to the next one? Okay, please.
Dame Sue Black had suggested a new kind of biometric based on the back of the hand. I've been following different kinds of biometrics, especially facial recognition, and I want to warn against a common mathematical fallacy that many policemen and courts are doing. Facial recognition systems today are 99.9% accurate. Given two images, only in 1 of 1,000 cases, they'll give you the wrong answer about whether it's the same person or not. Sounds fantastic. But police are using it to search through databases. And if you realize that there are 10 billion people around the world, there are going to be 10 million people who will be picked up as being as corresponding to the particular pattern that you are looking for. So you should never use any kind of biometric in order to search in databases. If you have a suspect and you have good reasons to think that suspect, if it's the relative of the child who was abused or anything like this, then you can use it. But be careful not to search through databases of the pictures of backs of the hands of people and then accuse them in court as the only kind of evidence.
So thank you very much for the summary for my plenary lecture on Friday, which was very, very kind of you, which is to say the difficulties that scientists have in managing the expectations of an investigative force. So police have an idea of what it is they want to solve. They don't understand the scientific basis behind it. And that's a real point of friction between us. And then further removed from that is when it goes into the courtroom, you're dealing with lawyers who often have no scientific understanding whatsoever, and you're dealing with an entirely different mindset again. And it's really important when you go into the courtroom to remember that you are the scientist, you are in control of the science, you understand it better than anybody else does in that room. And it's a very, very scary and daunting place to be as a scientist, because a courtroom, it's not your rules, it's not your game. You can only answer the questions you're asked. And if you're not asked the right questions, then you can't get the right answer across. And it is a very, very dangerous place. Now, I spent some time working with the Home Office in relation to facial recognition validation of software. And it was that very point that we said to them. You cannot just scan faces in the hope that you'll find somebody that you might think shouldn't be there. That's not what it's about, and that's not the basis of it. So we are 100% on the same track.
Okay.
Just to on a lighter note, on this question, of course, probability and bias sampling questions, it couldn't help crossing my mind that okay, I'm going to first say the tale and then say what I would want to apply it to is, imagine you have a jungle, which is, unknown territory in front of you, and you are saying, is it a dangerous place? So then people send 100 or 1,000 people into the jungle. Only 30 come back. And then you ask the 30 who come back, was it dangerous? And they say, no, it was absolutely fine. Very good. So 100% of the people who came back actually said, it's great, go for it, follow my advice, you can go as well. And of course, well, if you only ask the ones who came back, that's not really a very good way of sampling. So I just want to warn all of you here that you're going out in the world of research and science, and somehow on the stage were the ones selected, who came back unscathed. And tell you it's great, go for it. If you have an idea, everybody tells you it's wrong. Continue, believe in it till the bitter end, because actually, it turned out that, I thanks to the luck I had or something, it ended up being, useful. So you are all very clever and you know how to, make use of all the advice, but it's always very, difficult for, if you've been selected because, some system chose you as a good student, then you say, well, that selection system is really great, so, we are, of course, very biased representative of the real world out there. So don't trust too much to what we're saying.
Trust some with some probability, yeah. Okay, we have some more question there.
So thank you for the fascinating discussion. You were speaking about kind of that sometimes within your field, you have a question that requires an interdisciplinary approach. But I have a question regarding kind of the idea generation step, that many times there are tools or ideas outside of my field that I'm not even aware of that would affect the questions and my ability to answer questions that are interesting for me, but I'm not aware that they exist. So my question is whether you have any suggestions to try to be in a state where you're open to and in search for things that you are not aware of that will enable you to ask better questions.
Okay, thank you very much for this question. I think you are right. It's very important to find out the questions outside of your scope. Therefore, it's very important to attend this kind of meeting.
Yeah, I mean, maybe I can add that, of course, the world that you are in is very different than the one we grew up in. So this morning we heard, I also had this experience going, the library by accident, picking up a book, finding actually the answer to, that was like magic. Of course, nowadays you just Google or ask ChatGPT or, whatever, they are able actually to find, the possible relevant pieces of literature. If you ask the question, well, that might, be out there, that might be useful for your particular quests. So that's one aspect. Of course, the other part is, there's, finding the right question or thinking, and sometimes could be, say, if you are a mathematician, which is, of course, hopefully not too many of you are, then it's also just, disconnecting, right? If the weather's fine, you want to think seriously about something, go out for a walk, right? You're not going to be, think about it. You're not going to, after 10 seconds when it becomes difficult, going to, check your email or have any distraction. So try to focus, solely on it without actually disconnecting from all this input. So, there's this part of, gathering the information and then try to digest it and still use our brain as a tool.
Okay.
Thank you.
All right, thank you. Yes, okay, one more question there, then we're going to move on to the next segment.
Thank you. Hi, everyone. Xiaohui here. I'm a molecular biologist student working on cilia to understand cell motility. So I do agree with the panelists that there is interdisciplinary approach within field even. But I'm curious, thank you. I'm curious on the topic that there is like core and the threshold. So is it an and or mutually inclusive? Or if it is an and mutually inclusive, how do we actually balance between the two, working on the core as well as the threshold? Thank you.
Oh, right. How do you do it? Do you really mean how do you do it? Or do you mean why do you do it?
How and why as well, but most importantly, how to balance between the two.
The question is, does it have to be in balance? So, you will have individuals who have a particular way of thinking and working that are in the same field as you that are different to yours. So it doesn't have to be that one way is right and the other way is wrong. They're different. And any one of those can be at a threshold where a difference is made. So I don't think it's a how. I think it's a recognition of what kind of a scientist you are in terms of your approach. It might be that you are a sole core scientist and that is what you do. It might be that you're an excitable peripheral scientist on the thresholds. But it might be in the morning you're core, in the afternoon you're excitable because you've had too much coffee. It really does just depend on what works for you. Don't be rigid about it. I think it is about opening your mind to what the possibilities are. And back to the previous question, I think it's about talking. I think it's about communication. It's about not being afraid to put your ideas forward. And whilst I hear the sentiment about ideas that we might have and fear that we might lose them and somebody else is going to pick them up and run away with them, have every single idea I've ever had. And if somebody makes something out of it, good on you, because I think science needs a lot more kindness, a lot more sharing, and a lot more openness. And if we can find that level of a community amongst ourselves, and we're not worried about trying to be something we're not, or trying to hold on to something that isn't ours, I think we become a much more effective and a much better scientific community. So just listen to yourself, listen to your own heart, listen to your own head. You know what will work for you, what your place will be in your team. Don't try to be something you're not. Be true to yourself, if that makes sense.
Okay.
Maybe
Thank you
I
very
can
much.
just add one thing, which is that I think there's something which is common to all sciences, which is basically, what is the current core, in the sense that there's a lot of, fashion, and people, suddenly everybody goes into one direction and everybody follows in one direction. And then some parts that, used to be very, flourishing 20, 25 years ago have been left completely aside. And sort of, there is this idea of, nowadays everybody does that and that's the direction to go. And I think that aspect is something which is clearly, that the things that have been left aside should be revisited, periodically. And I think I often hear, we mathematicians are lucky enough not to have to discuss with editors of journals like Nature or Science about trying to publish our things, because we publish our things in math journals anyway. But I always hear from our colleagues that there is this question of what is recognized as, core, right? Sort of, and how do these editors, which are, professional editors and, not core scientists, going to decide that this is something that should be sent for review or not? And there, that's exactly where the fashion, comes in, because they say, well, now, everybody, we want to sell things to our readership, like a journal newspaper would do, and we have to satisfy our readership. They want to learn about this and not that. And so the sort of decision of what is important very often comes out of, the global, self-reinforcing consensus rather than for, directions that are a bit out of fashion, but then maybe what you might do is revolutionary in that aspect. So I think one general advice is not to forget that, what people have been doing maybe depends on your field, the cycles at which things are forgotten, but 10 years ago, 15 years ago, 20 years ago, 40 years ago in our area, there were great things, and if there are things that, if some area has been left a bit untouched for a while, then actually it's very likely that there are lots of things to be said there if people stopped working it just because the train moved elsewhere and everybody was following elsewhere. So I think there's this also question about what is the core. It's also very often, defined as, self-reinforcing thing, especially these days where all of us, we get exposed to very similar things. In the olden days, in the 70s, when you have the math physics school of the Soviet Union and the math physics school here and there, people were not communicating as much. And therefore, you had sort of, different type of inputs that people had. But now everybody has access to exactly the same thing, the same papers, posted. They read the same things. They will have the same ideas at the same time because they read the same things, and so there's a tendency to uniformization and to people going following the trend. And I think it's very important to try to be aware of that and try to counterbalance it. Yeah.
Thank you.
All right, so maintaining core while being at a threshold and define it as you like it. Sort of what the message is here is. Okay, so I think we're going to move on to the next segment. We have talked about the field, the threshold, the interdisciplinarity within the field. And now we're going to move on to more of a global problem and humanity in general. So I would like to ask the panelists, what is the biggest problem humanity faces today, and how do you think that the interdisciplinary approach will be important in solving those problems?
Let's ask the real scientists.
Okay. Yeah. Well, if you ask the biggest challenge for humanity, then my answer is, I think, climate change. It's getting more and more evident, even for a non-expert like me, that the effects of climate change is very serious. Well, on the other hand, it is an extremely difficult problem to, say, stop the carbon dioxide emission. Even if we stop the carbon dioxide emission now, CO2 should remain in the atmosphere or in the sea for many years. I don't know how many, but let's say 1,000 years. Then it's clear that we have to think about the ways to keep the Earth in a healthy condition as much as we can, accepting the real carbon dioxide level, in addition to make efforts to minimize and stop the emission. So clearly, scientists from various fields, of course, essentially all fields, including natural scientists, biologists, social scientists, engineering, and even humanity people, should work together and involving various stakeholders. So this is really an interdisciplinary challenge for us all.
Climate change is definitely something that is of concern. I just heard coming here today that there is a blizzard and snowstorm in parts of the world that was never seen snowstorm before and causing a lot of accidents and stuff. So this is definitely a main challenge that we are facing at this time and requires interdisciplinary approach. Any idea what those will be?
Yeah, so my
Or how?
my answer to your initial question is, well, the first thing, of course, is that, you know, let's put it, you know, my family background, parents, you know, they're humanities and historians, so I do care about problems. There are essential, you know, it's, one can wonder if there is a way to, you know, interdisciplinary or not, right? To, you know, if you pump out huge amount of energy in the atmosphere, it will hit back, and there's no, you know, and of course, you know, AI, and as soon as history shows that as soon as there was, you know, unbalance and new things, you know, mankind wasn't very good at finding a new sort of balance afterwards. So, but the only, I mean, the other thing that comes to my mind when you ask the question is that there was remember so I'm not going to answer it. I just want to say that I'm not qualified to answer it because and Koen Tanuji, who is a Nobel Prize in physics, got interviewed one day in on radio after having a Nobel Prize and asked, okay, what do you think about the state of the world and this, and then his answer was, well, I just got, you know, I'm just coming out of my lab where I've spent the last 25 years. It's underground. I've been in my lab for 14 hours a day, and who am I to know much about the outside world? You know, how qualified I am. So, you know, we are not necessarily, you know, very qualified to answer these very important questions. But the only thing which is we know for sure, if you do, you know, these models or, you know, phase transition type questions, or is that, well, if you pass a certain threshold, then there's no way back. And yeah, that's just not a very positive way to look at things. And I'm not sure that, you know, having the programmatic thing to say, yeah, interdisciplinary will actually solve it is just going to be the right way to do it. Having said that, you know, I've just coming back from Tasmania, which is, you know, where you have the actual untouched wilderness in half of the island over there. And, well, I'm sure there will always be, you know, some birds singing there, whatever happens to us. Yeah.
I'm not sure how to comment on that one.
You asked the question.
Okay, so there's a limit as to how an individual could project, I suppose, in terms of what is the global challenge and what is challenge facing humanity. But we know one thing: if we pass a certain threshold, there's no going back. Any more comments, Sue?
Any more comments, Sue? Thank you so much indeed. Most of the global challenges that we face are human-based and human-caused. Therefore, there has to be a human responsibility to resolve them, because nobody else is going to do it. And I wouldn't care to rank them, but we all know what the challenges are, whether they're associated with climate change, whether it's about energy, whether it's about food, whether it's about water, whether it's about population size. We know what the problems are. And half the battle is knowing what the problems are. If we are at the base of it, and we know what the problems are, then the collective brain power of humanity must be able to resolve them, providing there is a will to do so. And it is the will to do so. It's the collective will to do so that I think is the most important thing. And scientists working together, I think, give the greatest amount of hope that we can have to achieve it. But I absolutely agree with Wendell in that if we let it get to a threshold and we cross the threshold, it becomes much, much harder to bring it back. So better that we intervene now, knowing what the problems are, working together to resolve them. Because once we've gone beyond a threshold, then we'll have the ability to bring all three disciplines on this panel to the fore, which is the recovery of the deceased, finding a new planet to go and live on, and the probability on whether we'll survive or not.
Well put, Sue. All right, so that basically sums up this segment in terms of what is the biggest challenge that faces humanity. What is it? And then everything. And then I think the fact that we are actually here, we have been listening to many of the thought leaders in the field, and who are more informed probably than most of us. And then just understanding and being aware that they are there. Use your interdisciplinary approach to understand what the exact problems on the other side is. And then look in and find out how you can contribute actively. I believe this is very important to actually help us survive, not having to look for a new planet, not having to look at the diseases, and with 100% probability or 99% probability that we're still going to be here many, many years from now. So interdisciplinarity, I think by now you are agreeing with me that it is a very exciting thing. It's not a field, it's not a discipline, but it's an approach. And it's an approach that we all should be aware and we should know how to do it. But like many of you, I was trained as a disciplinary in a discipline. I was trained as a chemical engineer, then kind of like biology more than chemical engineering, so then I went and do biomedical engineering. Each one of the panelists here is also trained as a mathematician. I know that Sue doesn't like this this classification, like linear classification, but okay, but physicists and anthropologists. So then, as you had kind of brought earlier, how do we even balance that? I want to be known as an expert of X, but then my work and how the world has evolved, or the science has evolved, requires me to be interdisciplinary. So how, as a young person, sitting in this room, thinking about what am I going to do in this very solve the grand challenges, I need to be an interdisciplinary person. Do I really need to be an interdisciplinary person? Because I think Wendell doesn't like to be that way. So then how do we craft our own core or expertise while being seen as a collaborative person or whatnot?
I mean, one general piece of advice is, of course, that when I discuss with students, you want to try to bring something into the world, the system, science, and in some sense, you have to be really also listening both to the outside world, to the facts, to the science, learning, but obviously the interdisciplinary element is yourself. So you have to, if you want to think of what can I bring myself that others wouldn't, if you do something that somebody else would have done anyway, then the impact is just, so what is it that you have in you that makes you want to connect this and that, or in your it can come from personal history or motivations coming from this or that, but why is it that you want to connect that sort of? So it's not, so you both have to listen to the science, the facts, learn stuff, but also trying to figure out in yourself what is it that I will be able to contribute that others maybe wouldn't. Right? So what sort of thing can I follow up on that maybe the others are not so good at, or maybe the others haven't realized, or maybe are not interested in. So you don't want to be original in order to be original, but you have to have in mind that in some sense what you can bring new into the new insights you can bring will be just the way you are going to blend together the various inputs you have. So if you follow a multidisciplinary curriculum, you will have that blend of expertise together to make relations between different ideas, understand, aha, this is the same than that, this reminds me of this and of that, and therefore you can apply ideas from one discipline to the other. But in some sense, that's something that we are trained to do, as Sue was saying, as human beings, that's what we do all the time, right? When we learn, as babies, how space is around us by moving our fingers and discovering things, and then, how do we transform that information into our brain and our own personal perception of what, space is around us. So we are all unique in this way, in which we process the outside information from the outside world, and you have lots and lots of different ways of thinking, because you grew up in a completely different world than we did, and so you have different ways of thinking about space, because maybe you moved around in video games, and for you it's not a problem to understand three-dimensional manifolds or something, because you know that it's possible that if you go out of the roof you come back here. That's what you did in some video games, and so you have intuitions about things that we didn't have access to, and you will be able to contribute in a completely different way, because you have also other inputs. The other thing I think is really important is that might be not the spirit of the GYSS, but what the people on stage did. It's some time ago we had an idea, we proved something, we found something, did that experiment and stuff. So you say, okay, it's easy, I understand that. What's next, right? So you are going to, what was difficult at some point, or was very novel and appeared to be difficult at some point, then after some time it becomes very easy. So it's like when you study, at the year end, you feel it's complicated, and 2 years later, when you're further down the road, say, oh yeah, no, this is like piece of cake, I can explain that to anyone. And that's the same with science, so that what used to be novel and difficult, you can absorb it much quicker, and therefore you can really look for new questions, make new connections. But be true to yourself, and don't lie to yourself. If there's something you don't understand, don't pretend you understand it. Okay, maybe in public you can not make a fool of yourself, but in private, say, okay, this thing I don't understand, I really want to understand it better in front of the mirror. I don't want to lie to myself. And usually, very often, that's exactly by clarifying what you don't understand that you're actually going to make the progress, be it inside the discipline or interdisciplinary here.
Okay, thank you, Wendell. Professor.
Well, okay, thank you. I'm afraid I don't have much to add. In any case, in my opinion, even in the interdisciplinary approaches, your contribution as a scientist should be based on your expertise. Therefore, I think it's very important that you have your own core expertise. And in addition, you should open your eyes to wider problems so that you can find new and difficult problems that require interdisciplinary approaches. Well, maybe that's all I can say.
Defining the core is very important here. I think that's repeatedly also from the other panelists. So would you like to have any?
The only thing I would say is quite often when we're in a sort of situation like this and someone will come and ask a question, they say, this is a really silly question. There is no such thing as a silly question. A question is a question. It's something that somebody doesn't understand and you're looking for an answer. Have the confidence to ask that question, because the chances are there are a dozen people in the room wishing they had the confidence to ask that question in the first place. And the inquiring mind that a scientist has to have is about, it's the Rudyard Kipling 6 Wise Men. It's the who, what, when, where, how, and why. Those are the questions. And if you can get a who, what, when, where, how, and why to most things, my goodness me, have you moved forward. But if one of them's missing, the who or the why, don't be afraid to ask. There's no such thing as a silly question.
Very important in the inquiry of interdisciplinary research as well, to ask questions and never be afraid of asking questions. No questions is a silly question. With the last 10 minutes, I would like to invite you again to ask your questions to the panel. This is a very important. Please line up as you raise your hands. I think there's one at the back. It's coming down. Yes, okay.
And remember, there's no such thing as a silly question.
Yes.
Thank you,
Nice from.
for
Please go ahead.
your insightful sharing. I would like to build my question on something that Professor Kajita had mentioned earlier when talking about climate change. You spoke about the importance of multi-stakeholder cooperation in solving some of our global challenges. And when we talk about multi-stakeholder cooperation, we often talk about the partnership between governments, industry, non-governmental organizations, and even international organizations. To this note, I would like to ask my question, which is that I think this model is good, but perhaps not perfect, which is why we are having this conversation today. So for all the panelists here, what is your hope for the collaboration between ecosystem players to enable us to solve global challenges better? Thank you.
Any one of you?
Very difficult question. I don't have a good answer to your question. But since this problem is so serious, I think we should keep saying that this is a very important question, and we'd like to have more and more people who notice the importance of this question.
Does that answer your, any more comments?
Yeah, I mean, you know, the people of my generation, let's put it like this, you know, it's the climate change thing is was avoidable, right? I mean, they you know, and people of my generation are the one who fell asleep on the wheel, and I think that, you know, if scientists would have been more, you know, invested, more open to these questions, then maybe collectively we'd, you know, would have been able to be more convincing, maybe. But I think as scientists, there's, you know, certainly something we can do about it, that, you know, at least ringing the bell and talking to whoever are deciding about things, about the importance of the matter. But yeah, you know, apart from the fact that my generation is sort of is probably collectively guilty of not having done enough, there's not much I can say.
Okay.
Thank you.
Thank you. Next question. We're going to alternate from here and then this, okay?
Good afternoon, panelists. So my question to you is, since the real excitement about interdisciplinary is on the edges between different disciplines, could be the process of interdisciplinary within one person's own head, or nowadays is considered as only between or among a group of people? Because to elaborate more on my question, the panelists on the stage remind me of one person, Leonardo da Vinci, because he was one of the pioneers of modern anatomy, and he was interested in fluid dynamics, considered as physics, and also geometry, considered as math. So my question in another form is to look for the real excitement. How could we possible to actually think in a way that allows the interdisciplinary to happen within one's own head? Or if not, is modern science too complex for one person to actually master all of these fields at the same time? Thank you.
That's a really interesting set of questions. Thank you. When you go back to Da Vinci and the early scientists, these men of science, and they were men of science, were generally wealthy men of science, and they were the polymaths. So they had interests in all sorts of different fields, and they had the space and the time to be able to indulge in that. As time has moved forward, we've become more and more specialized and more siloed in our disciplines. And I think our own thinking and our ability to think laterally and outside the box has been impaired. But I think we're aware of it now. And there are two ways to do it. One is to find other people around you who complement your understanding but have a different perspective. But there's also the bit about don't be afraid to step outside your own box. So go and learn something that is totally alien to anything you've ever done before. Go and learn a foreign language. Go and learn how to play an instrument. Go and do wild water swimming. Whatever it is that is completely different to something you've ever done before, and expand your mind. We tend to try and expand our mind within our area of comfort. It's going outside your area of comfort that for me is the really exciting and challenging place. And we have a responsibility, I think, to do it to ourselves. We have a responsibility to find the people around us that will help us to do that, and we'll have the different disciplines. And maybe we'd have the best of both worlds, that we'd become the polymaths surrounded by fellow polymaths, everybody frantically excited about the opportunities with those multiple thresholds.
Yeah, one piece I want to add is that we got selected. We as good students, we are good at learning stuff when you are selected as good students. But somehow the curriculum is you learn stuff during a certain time, then you do a PhD, and you stop learning basic stuff. So, why don't you take every day 1 hour of your time to learn something different? Textbook of molecular biology if you're a mathematician, or astrophysics if you're a molecular biologist, and all this, it's all out there. You just have to Google, you get the information very easily. And to just, don't stop, your curiosity, because there are so many nice things to learn. If you're a mathematician, you can just continue learning other parts of mathematics and be, amazed by how beautiful, topology is if you are a probabilist and so on. But continue learning. That is really sort of the key, I think, to open your mind, and that also will give you the confidence to say, okay, I know nothing about this other field, but I can learn. And it's not because and I know I'm good at learning, so it's not because I wasn't trained as this or that I'm not allowed to pursue and catch up in that direction. So very often we try to define ourselves, say, I'm good at this because I've always done that. And that's a way to exclude people from the outside. And then if somebody from physics or something comes to tell me something I don't understand, I say, well, I don't understand your language, sorry, I'm not interested. But if I sort of know how to train my own openness and curiosity, that helps. And I strongly encourage everyone to, continue, learning, not just reading superficially a newspaper article or this, but say, okay, this part I'm actually interested in, I can actually start doing it. That's, I think, how interdisciplinarity actually really starts.
So everybody has the ability to be a polymath, but not everybody can make it. So, but one way to do it is to basically learn and then continuous learning, right? So that's sort of the message here. All right, thank you. So we have very limited time now, so we need to go on a speed questions and speed answers, okay? So let's go to the next one.
Hi panelists. Thank you very much for your candid sharing. So my question is that I think you talked about being true to yourself, about knowing what you don't know. But sometimes, how do you tell that it is you don't know something because it's new versus you don't know something because you don't understand? And to what And how do you differentiate the two? And sometimes when you don't understand something, it takes very long for you to even realize that you are starting to understand something. So how do and discovering something new is important because if discovering something that you don't know because it's not known is important because that's how you identify something as novel. So how do you all tell the difference in an efficient way given we have only 24 hours a day? Thank you.
Speed?
I mean, the speedy answer is, for me, is it's also important to learn what there's also a non-rational aspect, right? You want to learn what you like, and you like what you want to learn, and that's because also you feel you can contribute. So, so you can't learn everything, but if there's something central in the puzzle of what you are actually interested in that you don't completely fully understand, then you should really zoom in there. If it's something peripheral and you're not attracted to it anyway and you don't understand it, then maybe your instinct is correct.
Well, okay, then, my short answer is, if you have such kind of questions, I think you better ask experts on that field.
So knowing who to ask is also important there. Yes. Okay.
Thank you.
All right, thank you. Next, please.
Hi, thanks for the really nice panel today. Just to keep it brief, in the context of using interdisciplinary approaches to solving global challenges, necessarily at some point you're going to push up against public policy and people who actually make decisions. I was just wondering, at what point does it become our responsibility to engage with people who make policy? On what level? And do you have advice for people who are young scientists, considering that if I give bad advice to a policymaker that they don't particularly like, it's certainly not going to contribute to my H5 index, which will affect my ability to get funding in the future, or possibly even deteriorate your career?
A very simple answer, if I may, is make sure that your policymakers are scientists.
So if I'm not Singapore and I come from a country that doesn't do that.
These were quick answers. It is really important to make sure that science is properly represented within our policymakers. And I know it's very difficult in some countries and easier in others, but that needs to be the answer, because we can't have policy made about science where there is no understanding of the science. We just can't, and we shouldn't accept it.
Yeah, fully subscribe to that.
Okay, is that good? Thank you. Next, please.
Hi, I am Mitradip Das from India. Am I audible? Hi, I am Mitradip Das from India, and I wanted to know that how do you communicate your ideas to people who are outside your field or even to policymakers? Because often the languages spoken are very different, and getting that is difficult often for me, at least.
Communication of science is hugely important, and getting it across in a language that is understandable. In the courtroom, we learn how to do that because the scientist must be able to convey to the jury, and the jury are members of the public, an understanding so that they can make a decision. The responsibility is on us as scientists to make sure that we communicate effectively and efficiently, and we make sure that the right message gets across. It's all about communication for me.
It will require a lot of practice.
Oh, a huge amount of practice.
Yeah. I mean, the other thing is, I mean, just to because you are here, I mean, we have in the front row here some people who actually have been involved, our top scientists who have been involved in very, very high-level policy making. It is very important to want to encourage you to, my answer to the previous question would be, stand for election, to be a policymaker, because that's, in some sense, maybe how you can, as a scientist, then be able. So we need a certain threshold of scientists in the policy making thing. And also, I think it's very important for the community to value exactly that aspect, which is this time spent and communication, and that this should be, gratefulness of the entire community, of some of us, spending time and energy, to try to make an impact at the decision-making level. Yeah. I mean, the other thing is, how to give a talk to a general audience. I mean, you sort of have you'll see this morning we saw how to do it the right way, in the first talk this morning. Tomorrow morning you'll see the wrong way, that if you're mathematicians, there's no way to make it work. Yeah, we do just our best, right? With personal communication skills, but the main thing is we have to try to forget that you're really a scientist, so make up a story that is not really what you're supposed to do, and then try to convey in some sort of a passive way, impressionistic way, some ideas that just stimulate a bit of the imagination of the people in the room. That's okay. Now convey,
So in a way, it's like learning new things, learn how to be a writer, learn how to be an actor, I suppose. That's included.
Perform.
I
mean,
exactly.
Every lecture is a performance in some way,
Yeah.
as we know when we do these lecturings. And yeah, so you can play that game if you want, or a lot or not, but that's sort of part of it. Because at the end, you are, the audience has to recreate everything in their own way. So you just have to try to, provide enough stimulation in certain directions. And sometimes in mathematics, the most inspiring lecturers are actually the worst ones, because they make you actually, you really have to think whatever they forget to tell you about, and fill in the dots. And yeah. So it's not just a comfort thing you want to, being in an audience and listening to science is something where you have to, it's tiring, right? Normally at the end of a day, okay, a panel like that's not science, it's just like filling, time. But if you have an actual science content talk, at the end of the day, you are just exhausted, because
I think we have to
really
be very quick.
Yeah, very quick now.
Thank
Thank you so much, Wendelin.
Really quick, I promise.
Question.
Thank you. I'm Josephine Buckingham from the UK. My question is really just picking up on Professor Black's tongue-in-cheek comment about passing the question over to the real scientists. So I was wondering, how can we challenge this perceived hierarchy within the STEM fields, where some disciplines are seen as more prestigious, like physics and maths often, than the applied and life sciences? And how can we all ensure together that we have equal respect for each other and their disciplines in tackling the global challenges that you've discussed today?
For me, it's about just ignoring people who think they're better than you. But because everybody has a perceived hierarchy, it's their perceived hierarchy. And as long as you're a part of the team and the community that are making the difference, I don't care on the team who thinks they're top dog, quite frankly, as long as we get the job done. So I wouldn't challenge it. The only way to challenge it is not to give it oxygen.
And then show that you can actually do it better than they do, right? Okay.
Thank you.
All right. Again, showing your contribution is important.
Hi. Sorry. I'm Will. I'm the postdoc at NTU right now, and I was trained on the interdisciplinary program, Welcome program in the UK. Now, as I becoming a postdoc and start to become more independent in my research, well, I'm a molecular biophysicist, so my research is interdisciplinary on its own. And as I walk through my PhD and postdoc, I kind of have a help from the PI, so I can work as a bridge. So my field is almost like a bridge between like clinicians and others. But as I start to get an independence in my group, I find it very difficult to publish or get a grant, because, they said that, oh, you're not a biologist because you're a computational biophysicist, and you're not a computational person because you're too much as a biologist. How would you advise someone at my career stage, where I'm aiming to become a PI, that, you know, how would I get money as someone who sits very in between, very interdisciplinary, like as a bridging between everyone around me?
Yep, it's...
So I was in a deeply unpopular subject. And when I went into Oxford, they said, my goodness me, you've done really quite well, haven't you, for a subject that is so desperately unpopular, which I thought would made me feel very comfortable in Oxford. At the end of the day, I think it is about ensuring that you, again, are true to yourself, that you know what it is that you're doing. Anatomy is viewed as being, pun intended, a dead subject. But at the end of the day, because we took it and we applied it in a different field, we achieved Queen's Award Excellence, we achieved multi-million-pound funding, we achieved top, department in the world in the subject that we did. So even though you feel, I don't quite belong, and it feels as if, I've got nowhere to go, it is that thing about standing on the shoulders of giants. It is about that core. There will be parts of a subject that haven't been looked at. Go back and do it again, and you'll find that niche for yourself, but you have to keep searching. It's always about searching. If you stand still, you'll go backwards. It's about moving forward and searching, finding your place, finding the tribe that you belong to, the place that makes you feel comfortable. When you find it, then you will excel, because as has been quite rightly said, when you find what you're good at, that's what you do better than anything else. Just keep searching.
Thank you very much.
Thank you very much for all the questions. They have really addressed, I think, most of the concerns that the young people have, including myself. Not that I'm young, but... So then I had a question. At the end of this panel, I would like to invite all the panelists to give like one more. Anything else that you would like to say in the last bits? Or I should just summarize everything now?
Just be brave, be bold, and be yourself.
All right, Professor.
Well, the topic of this panel was interdisciplinary, but as I said, I think it's very important you have your own core expertise.
Yeah, I just want to thank everyone to keeping up with us for all this time. I sincerely apologize if we might have given the impression of, pontifying and, giving a good, saying truth, or, we are all, not so sure about things. We try to, do our best to answer a question, and again, stimulate imagination or things, so you can just pick a few things you heard maybe and might be, useful for you later, and put the rest in the bin. I don't mind. It's okay. But yeah, so thank you for listening to us.
Okay, thanks. Let's thank the panel, all of them again. So, wrapping up, just I hope that you all go away with a very crisp idea of what interdisciplinary is and how to operate. So first, you need to be honest to yourself, what you know, what you don't know. Trust your people, that scientists around you, all the people around you. Communicate, and learn how to communicate, very important. And define your core. Define your core is a very important thing. Ask questions and operate at the threshold where the things are most exciting. All right.
Let's put your hand together to thank Professor Lim, because she's managed to keep this panel going. Well done.
Thank you.